Okay, first off, I'd just like to say that I'm not a trained engineer, and I'm not a qualified scientist either, but I am a designer and a communicator. I've been very, very lucky over the years to work with some incredible people on now 3 space missions, and I suppose one of my superpowers, if you call it that, is joining dots together, joining people together, and actually being able to communicate what scientists are learning and then build that into engineering and build that into something that is monetised in companies. So over the last 6 years, I've worked with Professor Sarah Seeger at MIT over in the US. And during that time, I've worked on things like the TESS space mission, so the Transiting Exosurvey Satellite System, where I took the science from the scientists, turned it into data that the public around the world could understand. You know, why are exoplanets interesting? Why should we be looking at them? Why should we be studying them? Back in 2019, I got a call from Sarah, who was very, very excited, back towards the end of 2019, saying, there's something happening on Venus, we're not allowed to talk about it, don't even mention it at the moment, but I need you on a conference call to actually work out how we're going to create a project around what they'd found. And I was thinking, okay, what is this all about? And they were very nervous at the time to actually give any results or any published information out. And obviously in 2020 it became public knowledge that signals of phosphine were being reported from Venus in the atmosphere. And at that point in time, it was very much a race for people to try and understand, one, what was going on in the atmosphere, but also at the same time to actually create crafts, probes, things that could get out there and actually understand what was happening with the science. So in the papers that were released in 2020, there are lots of different theories about how life was evolving in the clouds. Was there life in the clouds? Is it microbial? Is it biological? What types of sort of interesting chemistry, exotic chemistry were actually happening? Because on Earth, we don't understand how phosphine is being created in the atmosphere on Venus, in the cloud layer. Now, the cloud layer is incredibly dense, and there is a section in the middle of the clouds that is called the habitable zone, the same that you have a Goldilocks zone in effect when you're looking at exoplanets and suns. It's just about the right type of atmosphere and pressures where something could exist. Now, bearing in mind that Venus, the clouds, are full of sulfuric acid, and it's completely off the chart on the pH scale as to how much acid is actually in the clouds. So you'd think that bioorganisms couldn't be living there. But yet still now, from 2020 all the way up to now, there is still this signal happening where phosphine is being created somehow. We don't understand what that is. So phosphine itself, in a natural environment here on Earth, would last about 5 hours and it starts to dissipate. So the fact that there is a constant signal, even though it's spotty, coming from something within the cloud layer, means that there is a chemistry happening that we don't understand.
Chris, if you're, don't forget, you've got two laptops going.
Yeah, thank you. So as I was saying, there are lots of theories as to how these microorganisms, if it's living life out there, is actually creating energy and then multiplying. One theory goes that Venus had seas at one point, the seas evaporated, and whatever microbial life were in the seas actually moved up into the cloud layer, and they were dormant for a period of time, and now they've been reacted. Other theories go to the volcanoes on Venus, and there's some sort of exotic chemistry reaction happening with things that are coming out of the volcanoes into the atmosphere and creating a type of chemistry that we don't understand here on Earth at this point in time. We just don't have the answers to it. So back in 2020, I was sat there with scientists from around the world, and this was during the COVID time, so this is all on a video call, and there's probably about 100 people in this call, everybody from JPL and NASA and Rocket Labs, talking about how could they get a quick mission out to Venus to actually study what is going on with the chemistry in the clouds. So I sat there through this meeting. It was about 3.5 hours long. People were discussing what is the cheapest and easiest way of getting a flight out there. And at the time, NASA was still miles behind looking at when they were going to start investigating Venus again, because it wasn't a priority, even though this phosphine had been found. And MIT had managed to get some funding from the Breakthrough Initiative in the US, Foundation, and they were looking at actually putting together a small lightweight mission that was a single probe that they could get using Rocket Lab's new rockets from New Zealand to Venus. And this would be the first time a private company would have actually gone interplanetary. So this is before SpaceX would get to Mars. Rocket Labs are looking to try and get to Venus. So it's very exciting in that respect. But all the way through this meeting, they kept on saying, we've got this one probe and one shot and one chance to try and sample something in the cloud layer itself. And they were looking at this probe here. It gets launched, the heat shield comes off, and basically this thing plummets like a bullet through the atmosphere. And the drop in total only takes 8 hours from start to finish. Oh, done. Sorry, 8 minutes, not 8. 8 minutes from start to finish. It's like a bullet being shot at a planet. And I kept on thinking, okay, so this is brilliant, the fact that we've got the money, we're going to do this, we're going to send this probe there, but if it's 8 minutes falling through the atmosphere, through the cloud layer, and they're going to use laser spectrometry to try and work out what was happening inside the particles and molecules that it came into contact with, if it hit a dry area in the cloud, or the wrong bit of cloud, you wouldn't get any information, no data back from it. So it was a real one-hit wonder. And at that point in time, lots of people on the call were saying, look, we need to try and somehow create smaller probes. We need to try and do something whereby we can slow down this one big probe that we're sending out there. And because Rocket Lab's rockets are small, there's not a lot of mass on the payload. So it's very difficult to start putting in lots of pyrotechnics, putting in lots of parachutes, trying to put in additional thrusters, anything that could actually slow the probe down. So the answer was posed, how do we create smaller probes that could be shot out from beneath or behind the heat shield and actually increase the flight time through the cloud layer itself, but also increase the sample area, but at the same time be cost effective. Has to be cost effective because this is a private mission. So over the course of the call, no one had come up with a real answer for it, and everybody went away saying, we'll have a think about it, we'll all regroup. And during that weekend, I actually was walking with my son, who was small at the time, through the woods, and I noticed, falling from the trees, sycamore seeds. And I thought, okay, it's like nature's answer. Could we use something to do with sycamore seeds and a single wing that was already deployed? Basically, you just release this thing, whatever it is, after the heat shield's taken out, and how long could it fall through the cloud layer? And would it be able to hold enough weight to actually sample and be a useful device in its own right? So went back to Professor Sarah Seeger and the team, and I said, look, I've got this idea. This might seem a little bit crazy, but I think we could do something around sycamore seeds and this single wing approach to create a spinning vertical vortices which will give you lift and slow the thing as it falls through the atmosphere. And the first thing she said was, you might want to try and patent this, and yes, we haven't thought about it, and it's yours, run with it. And I thought, what? Really? Hang on a minute, we've just been talking to NASA, JPL, all these other people, and yeah, the upshot of it was a unique idea that no one had actually thought about doing. So for the next 2.5 years from there, I started to put together a team and actually started to build out this, which is the Leading-Edge Vortex Lift, or we call them LEVL sample probes. I wanted to create something that would slow down as it fell through the clouds, but actually had enough mass and enough space to be able to create some form of sampling system as it was falling through the clouds. And at this point, I got Nick Jones, who's chief engineer over there, involved, thank goodness, to actually help me understand the properties of scaling up from a sycamore seed to things that actually fly at this size, which is where we got to. So we wanted to create something that actually could carry a reasonable sized payload, but at the same time could have a wing that would basically twist and fold up and then just drop out and then do what sycamore seeds do best, which is just spin and float and slow down as they go. So we were looking at putting a MEMS device inside something of this size. So we were trying to scale up from a sycamore seed and actually build something that big. And during the process, which was a year and a half of blood, sweat and tears, we created, so this is that one flying there that you can see, dropping from drones. We totaled 2 drones. We bought a giant kite from America. We nearly lost Owen, which is the small son there, because it was so bloody windy when we were trying to drop these things out of them. We nearly lost Owen. And I broke one rib as well trying to control the kite. So, yeah, science can be painful, but at the end of it, after 2 years of doing this, we had enough data to actually publish a paper, and MIT actually paid for the publication, and it went into the aerospace MDPI supplement, which was a special supplement on Venus. So we were then listed as being an approach to do additional sampling during the Venus LifeFinder mission. So we were in. Problem was, all of the data that we got from our first different sizes of probes that we were dropping, these LEVL probes, were giving us completely different readings. And we were trying to get something that would actually fly at a rate that we could predict. Because Professor Sarah Seeger kept on saying, this is a great idea, but how long extra is this going to give me in the clouds? Because the longer this thing can fly, the more information we can get out of it, and also the more practical experiments we can actually run inside the probe that we were looking at. With all of the research that we did over the 2-year period, we realised that you can't just scale up a sycamore seed. It would be great if you could just go, there's a sycamore seed, just enlarge it that big, and it will fly perfectly. It so doesn't work like that at all. I wish it did. I really wish it did, but it didn't. So what we've got here is a series of drop tests, and we've also got some data in there from Varshini, which was a paper that was studying the flight dynamics of sycamore seeds. So we put all of our data in against other people's data, and there was a lovely line that was supposed to go up lovely and straight and beautiful, but unfortunately our big orange LEVL probe is test article 2, and you see you've got this lovely line and this bloody red dot that's not actually staying on the line, so we can't scale stuff up. And at that point we both decided we needed more help. We just needed more brain power, more people to start looking at this problem. How do we scale these things up? And also, where should the centre of mass be? And how can we make them fly every time, no matter what the size of the probe? So this is where Exeter University comes in. So Vanshika, who's up there. So Vanshika's one of our students that's been helping us through Exeter University, and she's been building out a model that's looking at drag and lift on the wings. So she's been using Exeter University's wind tunnel and using a flat-shaped wing, and basically looking at the pitch. So as our LEVL probes fly, how much pitch should we have on the wing as it flies? And depending on how much mass you're putting on that wing, depends on how much weight then you're putting on that front wing, and how will it drag or will it actually lift. The more spin we get, the more lift we get, the thing will drop slower and slower and slower. So Vanshika's actually building out a model for us there. At the same time, we have Kate, who's in the room here as well. So Kate's helping us with modelling the wing using open foam, and she's creating a mesh model that will actually help us understand the forces on the wings, how the air actually moves on the top and the bottom, but also at the same time how it moves in 3 dimensions as it rotates and how those forces change. So Kate at the moment is building out a model doing that as well. Last year we had Tom Boxer, who actually, he's now left, he's graduated, and he built a series of small LEVL probes. And he spent a good couple of weeks, I think with UK as well, didn't he? In the Great Hall, just across there, the big building you might have seen, throwing off, where was it, the top of ladders or something? Top of a balcony, throwing these probes off continuously and actually monitoring them as they fell, and changing the mass, where the mass, the centre of mass would be, and changing the amount of weight on that leading edge to give us more data again. And Tom's work actually has helped us build a model. So now that we can start to understand the dynamics of where the centre of mass needs to be and how heavy the leading edge needs to be to give us just the right amount of lift. So as things fall, They start spinning and they lift back up again, this vortex that helps lift our LEVL probes. So that's happened over the last 2.5 years. At the same time, MIT have been building up funds to do larger missions to Venus. So they started off with the idea of just doing one single shot, which was Rocket Labs. But since then, they've actually built out a whole series of what they're calling habitable missions, which are the Morning Star missions. And that's using one giant parachute with one large probe, which then can have smaller probes released from it. But also they're looking at floating a balloon in the atmosphere as well, which again gives us a lot more scope for using our smaller probes if we have a balloon floating through the atmosphere, because it means we can relay stuff back and then get it back to an orbiter. So from our original idea of we're just going to build a probe and do some experiments on the fly, we ended up with a new series of aims from Professor Sarah Seeger. So some of the main experiments on the chemistry that's going on inside the clouds will be performed by the larger probe, the mother probe, but then our probes, as they were falling, needed to do some very specific things that they wanted to find out about to try and start to map the environment inside the cloud layer itself. So the first one was, we have to measure large-scale winds. There are a lot of winds on Venus. It's not just a case of being a horrible environment with lots of acid. The winds can be incredibly strong in the cloud layer itself. We also want to measure small-scale turbulence. We also want to look at the acidity at high and low altitude to try and work out how this habitable zone that they're talking about within the cloud base actually works. So where is this chemistry happening? And is it too acidic towards the bottom or in the middle? Or actually, what is the acidity range? Which is all the good stuff that our probes will actually do. So we've managed to go, and also temperature and pressure. So we've managed to go from things that are this big, that were really struggling to actually fly. So this is our first public showing, actually, today of our new version of our probe. So it's still the LEVL probe, but we've gone from that to now something that we know will fly. And we've actually packaged all of our telemetry, all of our acid sensing down to a very small pack. And again, Nick, who is our chief engineer, has worked tirelessly hard on this one. So now what we're doing is we're using the wing, which is actually the PCB, in effect, to create a LEVL probe. And this is the size of the probe minus the payload, which is a bit heavy at the moment, that we're looking at deploying now, which means that we can pack lots of these together very, very tightly and deploy lots of them simultaneously. So as I was saying, it's very small mass. You're looking at 20 grams per probe, which is brilliant when you're trying to pack them into a larger mission. So it means for the mission architecture, it's a great weight saving in the first place. They're only 20 mil in wing length. We can pack up to 60 probes in a very, very tight space, which actually, once you put the container and all of the radio support in, only gives you a complete mass for 60 probes, 2 kilos. We can half that if we want to, just by putting 30 probes in rather than 60. But we've managed to create something now that will actually work as part of the mission parameters itself. And we couldn't have got to this, actually, without the help of Exeter University and the work they did with creating models that helped us to identify exactly where the centre of mass needed to be to make these fly perfectly. So now we can design stuff that fly pretty much every time. The PCB board and how the LEVL probe works. Obviously, we've got the batteries and microprocessors, which are attached to the PCB board. We then have a top-style pH measuring system, and I'll come back to the top system. We've got a few slides on that as well. We then have a motorised release mechanism. Now, bearing in mind that these things are flying through acid constantly, we don't want the sensor array to be, basically wiped out as soon as it hits the clouds. So we've created a system whereby it's peeling off a layer of protective film, which means we can decide exactly where and when we want to take the measurements. So we can start by dropping 60 and have some of them take them at high measurements, some have taken the middle, some have taken the low points in the cloud layer as we go through, which obviously gives MIT and also scientists the data that they need. We also then have an autometer in the centre. Again, this will help with everything to do with the wind speeds and the pressures. And then we have our radio system to fire everything back up to our mother probe, which would be a balloon. This then shows, because the way in which these have now been designed, it means that we can pack them really, really smallly in a small, tight space. So they overlap each other, which means that in a very small space, we can actually pack 60 in incredibly tightly. Now, as I was saying, using Exeter's data that they've compiled to create this model for flight for our LEVL probes, it means that we know when we've created this and started to actually run our own tests on it, it wasn't a guessing game. With all of our first probes of the first 2 years in the paper that we released, everything was trial, error, trial, error, trial, error, whereas now we're creating probes that we know that they fly first go. So the probe that I've got here, which is a prototype, actually has data logging in this LEVL probe. And it means that we've been doing drop tests over the last, how long have we been doing it now? 6 months?
January.
Yeah, since January, okay. Since January. And the data we're getting back on this is really useful. So, we've got linear acceleration across the top. We then have our rotation in the middle. And then we have a magnetometer on the bottom. And what we get is they fall very, very quickly to start with, and because of the pitch and the rotation and the centre of mass, they soon start to spin. And as they start to spin, they then start to lift and slow as they're falling through. So we're actually getting a lovely wave line happening here, which is them starting to rotate as they go. So part of what we want to do for our next phase of work is actually look at how we get more of these deployed higher up in our atmosphere in the UK or on Earth. So we're looking at everything from weather balloons to helicopters to actually start flying more of these out to do the proof of concept for the next stage. From dropping these, doing our drop tests, it's given us some rough data that we can then use to actually scale up to have a rough understanding of how these things will work in the atmosphere on Venus itself. So at the moment, we are looking at, where are we? The average fall in speed is 4.6 metres drop height, and that drops through at about 2.5-ish metres a second. When we start scaling that up and then putting in the atmosphere, which is different on Venus, we can then start to calculate how long these give us from sample time. Now, you remember at the start, we were saying that the probe they were going to send was just 8 minutes. Bullet. That's it. Done. Well, we're now calculating that these will actually give us a flight time of around about 80 minutes through the cloud in total, which is a massive area of sampling that we can now produce and achieve using our LEVL probes. Obviously, at the start of the atmosphere, it's very thin, but as it starts to hit the cloud layer and go through, the atmosphere gets thicker and stickier and thicker and stickier, which actually helps us even more with our probes as we go through. So we're calculating at the moment 80 minutes flight time. And we're also looking at building out models again with Exeter University to start looking at the atmosphere as a whole around Venus so we can get a better understanding of how well they will fly. So I was talking about the TOPS. So the TOPS pH sensor is from the, I can never pronounce it, the Tartu Observatory pH sensor system. So it's something that's already been developed, and it's a very, very clever way of using chromophore and shining light through a chromophore, and the chromophore will then fluoresce. And depending on the colour that fluoresces back from it, you can then get a reading of your pH. And the pH levels using this system can be incredibly high, to the point of they're not really acid anymore, but you get a really good understanding of the depth of pH that you can actually scale. Now, the problem that we had to begin with was, how do we take something that's a technology in a camera that's quite large and scale it down to something that's going to fit on a 20-gram LEVL probe? And Nick, very cleverly, has managed to take apart flatbed scanner technology and actually re-engineer it into our leading edge. because our leading edge on all of these sycamore seeds, when you look at them, or a LEVL probe, the leading edge is always the heaviest part, and then you've got the nut itself, which gives you the tilt, and then you start to rotate. And we want to use that leading edge as our sensor array. So how does it work in practice? So we have our leading edge, as I was saying, but that actually is a light guide that's covered in chromophore. And the chromophore is this chemical that will actually react with an acid, and then once the light shined at it, you'll get a different fluorescent back of colour, different fluorescent colour. You then have a PTFE mask layer which covers our sensor array, in effect, and then you have a motor. And as it falls, and we can do it through time, we can do it through pressure, we can do it through altitude, we can choose when that layer is actually peeled off, and then take our sample reading from there. So as I was saying, if we're going to drop 60 of these, we can do them at completely different altitudes as they're going through the cloud layer. We've then got an LED which illuminates the back of the chromophore itself, and then that light is reflected back through, hits a lens, and then finally, where we're here, we've got a CMOS sensor right at the back, which is connected to the PCB on the motherboard, on the wing itself, which picks up the colour that's being reflected back. And all of that is fitted just in this little narrow strip here. But when it's working together, we can then do pH readings at any altitude that we want to in the cloud layer itself, which was one of the key questions that MIT posed to us. Is this possible, and can it be done? One of the other things that MIT asked us to look at the time as well was the winds, and actually how are the winds working? How strong are they? You know, what's not so much what are creating them, but what patterns are they getting, especially in that habitable zone area within the clouds itself. So we were looking, because we're going to release 60 of these very small light probes, we wanted to try and track them. Now, trying to track them on a planet when you've got nothing else around is very, very difficult to do. So what we actually use the mother probe, which will be a balloon, and then we ping between each one of our probes as they fall. And that starts to give us some idea of where they are in relation to each one and other as they're going down through the clouds. So what you're seeing here is an illustration, not a simulation at this point, but you start to get an understanding of how these very small little level probes start to talk to each other to create shapes and patterns. And the shapes and patterns are crucial to understand how the winds are working inside the cloud layer itself. So we answered one of MIT's other questions, which is, can we do wind scale, and also can we look at the turbulence inside the clouds? And using up to 60 of these together as a swarm, we can actually do that and map the clouds and the wind within the clouds itself. So now we've got telemetry on pressure, temperature, altitude, acid, and actually the structure inside the cloud layer itself. So that's what we've been doing with Exeter University to this point. Obviously, Jane Greaves discovered the original phosphine signal back in 2020, and that was Cardiff University, which is in the UK. And we're based in the UK, and it's really nice for us to sort of go full circle and stay part of missions that will be moving forwards to try and explore more of what's happening in the clouds on Venus itself. At the moment, we're looking for additional funding to actually start building out the programme to look at manufacturing and packaging of the LEVL probes. But we're in talks at the moment both with ESA, NASA and MIT for all of their missions, which are slated around 2029 to 2030, to actually have some of our LEVL probes as part of their programme. I probably sped through that far too fast, I'm not sure. But anyway, that's me. Thank you. And